Hi guys, Mrs. Geiger here. So I am recording your Unit 4 bonding review. I'm going to do a separate review for naming compounds. And so this will just cover bond types and all through types of solids, including intermolecular forces. All right, so bonding. Remember that a chemical bond is a mutual simultaneous electrostatic attraction between the protons of one atom and the electrons of another. So simultaneous means that the two atoms are attracted to each other at the same time. All right, so all chemical bonds are a type of attraction of atoms. Now, the first thing we did was we talked about how to draw Lewis electron dot diagrams, and don't forget that when you draw a Lewis electron dot diagram for an element, you are just going to be doing the number of valence electrons. So remember on that quiz you did the oxygen Lewis electron dot diagram. So that is how we draw just an element, just an atom by itself before it's bonded. And then we started talking about the different types of bonds. So the first type of bonding that we talked about was ionic bonding. Important points are that electrons are transferred. It is between a metal and a non-metal. And you always form two different types of ions, a positive ion and a negative ion. Now, sometimes, depending on the type of compound, you might form more than one positive or more than one negative. So example would be calcium chloride is CaCl2. So in calcium chloride, we form one positive ion, but we form two negative ions. So this doesn't always have to be in a 1-to-1 ratio, but it always will form positives and negatives. Now, it's important to remember that the attraction is due to the fact that they are opposite charges, right? Ionic bonds form ionic solids. That's easy to remember because it's the same term. And don't forget that ionic solids are also called salts. Right? Salt is a general term for an ionic solid. Ionic solids are always neutral in charge because all of the positives in the cation and all of the negatives in the anions always add up to 0. That shows a conservation of charge. That shows that the same number of electrons that are lost by the metal are gained by the nonmetal. Now, there is a threshold. This 1.7 value, you can subtract electronegativities and determine if they're different enough for the electrons to be transferred. So if the electronegativity difference is very, very large, the electrons are going to transfer to the element with the greater electronegativity. The atom with the greater electronegativity will become the negative ion. Electronegativity negative, all right? Greater electronegativity negative. So when you subtract the electronegativities between the metal and the nonmetal, if you get a value that is greater than 1.7, that tells you that it's going to be an ionic bond. So we did NaCl as an example here. These are always absolute values, by the way, so it doesn't matter how you subtract. You should always subtract the larger value from the smaller value to find out if there's a difference of 1.7. So ions are charged particles. They're formed through the transfer of electrons. So atoms become ions when they gain electrons, become more negative, or when they lose electrons to become more positive. But this does not always happen in a 1-to-1 ratio. So you can remember our example of aluminum oxide. Aluminum has 3 valence electrons, and oxygen has 6 valence electrons. In this example, the aluminum has lost its 3 valence electrons. So this atom of aluminum will lose 3 valence electrons, 1, 2, and the third one is here. And that's because oxygen is going to react by gaining 2 electrons, so it has a 2- charge. So overall, you need 2 aluminum atoms and 3 oxygen atoms in order for 6 electrons total to be transferred. You can write this also like this, where we put the big coefficient out in front so we don't have to redraw that diagram over and over again. And that tells us that the chemical formula for aluminum oxide is Al2O3, where there are 2 aluminums for every 3 oxygens. Next, we moved on to covalent bonding. Covalent bonding is when electrons are shared, and this usually results when a nonmetal bonds with a nonmetal. Now, this can either be the same nonmetal bonded to itself, which would form a nonpolar bond, or it can be 2 different elements bonded to each other, which would form what we call a polar bond. So, we're talking about just bond polarity here, where we have I2 and hydrogen iodide, and you can see that in this example, the I2 is nonpolar, but the hydrogen iodide, the Hi, is polar. The iodine has a greater electronegativity than the hydrogen, and so since the iodine has a greater electronegativity, it's more negative. All the electrons are on this side of the molecule. Now, here, you can see that the hydrogen, its electron is on this side, so that means that its nucleus is right here, and that means that this would be the positive side of this molecule. This is the PhET simulation, and here's an example of a molecule that reacts similarly. Since iodine and fluorine are both halogens, they're both in group 17, I picked this example to show you how a HF molecule would look, where this side of the molecule is much more negative because it's pulling on the electrons, while this side of the molecule ends up much more positive. Don't forget also, I'm just going to move this over, don't forget also this idea of a dipole. Dipole means that there are 2 poles and that one side of the molecule is more positive while the other side is more negative. And we always draw those vectors going towards the more negative side. Now, in this example, the bond dipole is going to be the same as the molecular dipole. Those vectors are the same size because it's just made up of 2 atoms. H2, on the other hand, looks more like this, where H2, because the 2 hydrogen atoms are equally sharing those electrons, neither side becomes more positive or more negative, and instead we have a non-polar bond. So, when I click on bond dipole, nothing happens. We don't see any dipole because this molecule is non-polar. It does not have a dipole. So when both elements have a relatively large electronegativity, they're going to share their electrons and they overlap their octet. They overlap their valence orbital to achieve an octet, and we call this overlap a covalence. So the electronegativity tells us which element is stronger. Here is more polar and nonpolar. We spent a lot of time talking about polarity. All right. Covalent compounds are called molecules, so covalent bonds form molecular compounds. You have to remember that definition. It's very important. Now, bond polarity can tell us the polarity between 2 atoms, but when we make molecules, we need to look at the overall shape of the molecule in order to determine the molecular polarity. Oh, snap! When a molecule is symmetrical in shape, it is going to be considered nonpolar. All right, so when a molecule is symmetrical in shape, all of the forces cancel each other out, and it ends up having no dipole, not one side of the molecule that's positive while the other side is negative. If a molecule, on the other hand, is shaped asymmetrically, the forces don't cancel each other out and they add together. And when that happens, we end up with this net force or a dipole moment where one side of the molecule is negative while the other side is positive. When I say waters, you say waters. Oh, polar. Right, so water is polar, and here is that diagram. So here is what we call the ball and stick model, where we're representing those shared electrons between the oxygen and the hydrogen as a line here, or a stick. Now, if I show the electrostatic potential on here, what you can see is that this is a lopsided molecule. And the oxygen side has all of this negative charge, where the hydrogen side ends up being very positive. That's because of the asymmetry. Because this molecule actually has lone pair or unbonded electrons around the oxygen here, like we see here, like we see here in this Lewis electron dot diagram, we see that there's these electrons on this side of that water molecule. So when we take a look at this version, we can see that those electrons are here and they're taking up space and they're pushing the hydrogens down, and this side of the molecule is very negative. CH4 is an example of a molecule that is nonpolar because it is symmetrical. So here is that electrostatic view, and you can see that it hovers right in this in-between region. I'm going to change this view here to show you that there are polar bonds. Each bond is polar, but because of the shape of the molecule, they all cancel each other out, and we end up with no overall net dipole moment on this molecule. So when I click on this molecular dipole, nothing happens because there is no dipole, because this is a non-polar molecule. I'll contrast that with the water molecule that I just showed you. And what you can see on that water molecule is that the negative charge is going to be on this side of the molecule because of the pulling of the oxygen in this direction and the asymmetry of this molecule. The next thing we talked about after we talked about polarity was the concept of a molecular shape. There are 16 shapes that exist, but you only need to know 4 of them. They're linear, bent, tetrahedral, and trigonal pyramidal, or just pyramidal, just special kind of pyramid. So that's what you should remember. So from the Lewis dot diagram, you should be able to determine the shape of all of these example molecules there. Some honors material here. We talked about 2 terms, the term ligand and the term domain. Anything that is bonded off of the central atom is called a domain. That tells us the general or apparent geometry of the molecule. Water, for example, has 4 domains. It has 2 hydrogens and it has 2 lone pairs. Lone pairs are electrons that are not bonded. So lone meaning not bonded, and pair meaning that there's 2 of them. My favorite oxymoron is a lone pair of electrons, but water has 2 of them. Now a ligand is when a domain is another atom. So ligands are how many atoms are coming off of the central atom. So for example, I'll go back up. In a bent molecule, you have 4 domains, 2 lone pairs, and 2 ligands. In a tetrahedral molecule, you have 4 domains, and all 4 of them are ligands. Now, these terms, ligand and domain, don't appear on the reagents, and you'll never see them on a test, but I use them, so it's worth noting here. All right, so the next thing that we did after we talked about molecular shapes is that we talked about this idea of intermolecular forces. Intermolecular forces are the forces that hold together molecules, not hold together the molecule like the hydrogen and the oxygen inside of the water molecule, but from one water molecule to the next molecule, so between 2 different molecules. So that the forces of attraction from one molecule to another molecule, and remember molecules are always covalently bonded, so intermolecular forces only apply to covalent substances. And this depends on the shape of the molecule. And don't forget that the shape determines the polarity, so you can also say that it is determined by the polarity of the molecule. So there are 3 types of intermolecular forces that you need to know. The first type is called London dispersion forces. London dispersion forces explain why nonpolar molecules disperse or spread out very far from each other. This is the weakest force of attraction. Nonpolar molecules don't stick together because they don't have oppositely charged parts, and therefore they tend to spread out easily. London dispersion forces are the only forces that are acting on nonpolar molecules. Technically, London dispersion forces act on all molecules, but when molecules are polar, those polar forces overpower the London dispersion forces to such a degree that we can neglect these forces. When you're comparing 2 nonpolar molecules to each other, the one that is more massive, the one that is bigger, will take more energy to push apart, and therefore will have a stronger force of attraction. So the first one is called London dispersion. The second kind of interaction is called a dipole-dipole interaction. Dipole means that there are 2 poles, and all polar molecules have a dipole. They have one side that's positive and one side that's negative. And here I have the little lowercase delta, which is the symbol that we use for dipole. The last kind of intermolecular force is hydrogen bonding. Hydrogen bonding is the strongest force, and it's actually a special kind of dipole-dipole interaction where you have very, very polar molecules, and that gives them specifically strong intermolecular forces. Now, hydrogen bonding is misnamed. It's not actually a type of bonding. It's a type of intermolecular force. It's really important that you don't mix that up. The Regents will try to fool you on that. When hydrogen bonds with oxygen, or hydrogen bonds with nitrogen, or hydrogen bonds with fluorine, there is such a large electronegativity difference that the molecules become extremely polar. This causes the molecules to stick together more than they normally would, and we call that hydrogen bonding. The most important molecule of all is water, and water-hydrogen bonds. The reason that water-hydrogen bonds is because it contains hydrogen and oxygen. So it has all of its negatives on one side and all of its positives on the other. This causes water to have these really weird structures where it creates this kind of honeycomb. I'm going to erase the hydrogen bonds so that you can see that these are molecules next to each other. All right, so each of these molecules is attracted to the next through a special strong force called a hydrogen bond. Because of the shape of water molecules, they form these like honeycomb shapes, and that is why water is the only substance that is less dense as a solid than it is as a liquid. As water freezes, it expands, and that's very different than every other substance. Every other substance, as you go from a solid to a liquid, the particles get further apart. But in water, solid particles have these like bubbles in them that make them further apart. So you'll remember that because water is the most important and the most unique. Now, if we were ranking our intermolecular forces, London dispersion is the weakest, then dipole-dipole, then hydrogen bonding is the strongest. This is also the trend in melting or boiling point. There's the same trend because both of them are referring to the idea that the more attracted the particles are to each other, the more energy it takes to pull them apart. So the more polar a substance is, the stronger the intermolecular forces, and the higher the melting point, and the higher the boiling point, because both melting and boiling mean that the particles are getting further apart. We also talked about how ionics would fit onto this scale, and that the least polar molecules, the least polar molecules are nonpolar. They have the weakest forces of attraction. Then we get into polar, and the greater difference in electronegativity there is, the more polar the molecule is, until you reach this threshold where the electrons are transferred, and then you get into ionics. Ionic substances are even more attracted to each other than polar covalents are. So the greater the difference in electronegativity, the higher the melting point of a substance. We also talked about types of solids, and we did a lab where we melted 4 solids. Actually, we only melted 2 of them. We melted the molecular solids. We saw that the ionic solids were so attracted to each other that they did not melt. So we know that molecular substances have low melting points. Ionic substances, which are also known as salts, have very high melting points. And metallic substances have what we consider medium melting points. Network solids were the 4th type. And network solids, your example is diamond. So for diamonds, they have extremely high melting points because of their unique structure. And we talked about physical and chemical properties as well. Don't forget that the ionic substances are made out of positive and negative ions, and they are hard, and they conduct, but only when the particles are moving. The particles are not moving in a solid, so solid salt does not conduct electricity. But if you make it into a liquid or a gas, or you dissolve it in water, it will be conductive because those charged particles will be able to move from one place to another. Molecular solids are soft and malleable. Your example of an ionic substance is table salt, NaCl. Your example of a covalent substance is sugar. Sugar we consider to be soft because we can very easily make it into a powder. Also, we looked in the lab at that paraffin wax, and you should have seen that that is a soft substance. Network solids, our examples are diamond. They are hard and they're non-conductive. All molecular substances and network solids, since they're covalently bonded and made out of nonmetals, they are poor conductors. They're good insulators. Metals, same properties as when we did the periodic table unit. They're malleable, they're ductile, they have luster, and they are good conductors all the time. We also talked about this term, allotropes. Allotropes, like carbon, can mean that it can come in different structural arrangements. So an allotrope is when you have the same substances that are made out of the same element. This applies to network solids. Made out of the same element, but since they're bonded differently, they have different properties. So the difference in their bonding makes them have different properties, which is why we give them different names. The most common example that you have to know is diamond and graphite. Diamond comes in this network where it's tetrahedral, which makes it very, very hard and very strong, whereas graphite comes in these sheets, and that's why it's easy to break your pencil tip, and as you write, you scrape off those atoms of carbon onto the page. The other 2 examples that we talked about were phosphorus, which is a nonmetal, and that's why it forms a network solid, or oxygen, which can be O2, oxygen, or O3, ozone. So it's just that they're bonded differently, which gives them different properties. All right, and the very last thing that we talked about was this idea of a polyatomic ion. Poly means many. So a polyatomic ion is an ion that is made out of more than one atom. Now, table E is on the reference tables. It's deleted from the honors reference tables. Ooh, I lost my S and selected there. It's deleted from the honors reference table, so you have these memorized already. But I'm going to show you how the table is organized. The first 3 are all of the positive ions. Then after those come all of the negative ions. All right, so there, all the positives are first, and then all the negatives are second. The negative ions are in alphabetical order. Well, kind of, they're grouped. So first, I want to point out that the acetate ion has two different ways that you can write it. This is two formulas that are identical in that they both have 2 carbons and 3 hydrogens and 2 oxygens. This bottom one is what we call the condensed formula. It not only shows you what it's made out of, but also kind of how it's bonded. And organic chemists do that, and this is an organic polyatomic molecule ion, and that's why this has 2 ways of being written, but they're identical. You can write either one. Then they're in alphabetical order, but you'll notice that they're grouped. So carbonate is CO3 2-. Hydrogen carbonate is when you add a hydrogen on to this ion, the charge changes from 2- to 1- as you add that H+ on, and it gets the name hydrogen carbonate. So we put those together because they're related to each other. These 4 are also related to each other. Chlorite and chlorate, the ending of ITE means that there is 1 less oxygen, and the ending of ATE means that there's 1 more oxygen. So, ite and ate. Now, hypo means below, so hypochlorite is even below chlorite with only 1 oxygen. Per means above, so it's above chlorate, so this is called perchlorate. So that's why these are grouped together. You'll see also nitrite and nitrate are grouped together, and sulfite and sulfate, as well as hydrogen sulfate, are grouped together. So kind of alphabetical, but grouped by also by classification. Now, polyatomic ions consist of a nonmetals that are covalently bonded to each other, but have a charge. So they ionically bond to other substances. So whenever you see a polyatomic ion, that molecule always has both covalent and ionic bonding. The example that we did was sodium hydroxide. Sodium hydroxide, the sodium is going to react by losing 1 electron. There it is. Hydroxide is an OH with a -1 charge. The way it gets a -1 charge is by gaining an electron from a metal. So there's ionic bonding between the Na+ and the OH-, and there's covalent bonding between the oxygen and the hydrogen. So this is how sodium hydroxide would be written. The next example that we did was ammonium chloride. What you'll notice in ammonium chloride is that actually this happens because an HCl and an NH3 come in contact with each other, and the hydrogen gets lured away by the nitrogen's extra electrons here. Hydrogen leaves its electron behind and forms 2 ions. This is an H+ ion because this hydrogen has 1 fewer electron than it started out with. And Cl is a -1 charge because it gains that 1 electron. So here's an example of a positive polyatomic ion. And this is an example of a negative polyatomic ion. And lastly, we talked about metallic bonding. Metallic bonding is known as a sea of mobile electrons. It results when a metal bonds with a metal. Now, this could be a pure substance where it's the same, it's an element where it's just 1 metal, or it could be an alloy where there are more than 1 metal. Alloys are not on the Regents. I gave it to you in your notes because I think it's important that you understand it, but it's not going to be on the test and it won't be on the Regents. So electrons are mobile, which means that they are moving. This movement causes electrons to be good conductors of electricity, and they will always appear on the left side of the periodic table. This is referred to as the sea of mobile electrons as they are moving. And actually this idea that there's this electronic fluid, the electrons are able to move and flow, is why we measure how fast the electrons flow through a wire is called the current. So in electricity concepts, this sea of mobile electrons is why we use the same term to talk about how fast a river runs as how fast the electrons move through a piece of metal. Both of those are called the current because we can think of the electrons moving like a fluid, something where the particles can move from place to place. Now the positive cations, the nucleus and all the core electrons, stay put. But the valence electrons are free to move from atom to atom, which allows metals to be good conductors of electricity. And that's it. That's the whole bonding unit in 30 minutes. It will be a different video for naming compounds, but that will in. Okay, good luck studying, and see me for extra help if you need it.